My name is Michael Kaiser. Today, I will be presenting my project investigating curvature-induced circumferential drifts to improve the 3D reconstruction of a deployed stent done under the mentorship of Lucas Timmons. Coronary heart disease is one of the leading causes of death in the United States. It is caused by a buildup of plaque that restricts blood flow in the arteries. Typically, clinicians can insert stents and reopen the blocked arteries. However, stent failure can occur, and an accurate 3D reconstruction of the deployed stent can be used to better understand the effects the stent has on its surrounding environment. Figure 2 illustrates the process to create a 3D reconstruction of a deployed stent. First, an optical coherence tomography scan of the deployed stent is performed. These OCT images are then processed to identify stent struts in each image slice, as shown here. This information, combined with an angiogram of the stent and vessel, can be used to orientate the stent struts in 3D space and create an OCT point cloud, shown here. Meanwhile, a micro CT scan of a stent of the same geometry can be performed, and then this can be turned into a graph and node structure. This structure can be bent to match the OCT point cloud, and this creates the final reconstructed stent with the correct geometry matching the deployed position. The previously described framework works well in an experimental setting. However, when the stent was deployed in a real vessel, circumferential drifts due to the curvature of the vessel were observed. This can be seen in Figure 5, where the micro CT ground truth has no drifts observed, but the reconstruction changes in position. The aim of this investigation was to understand the relationship between vessel curvature and the circumferential drift of the acquired OCT imaging data. To better understand the relationship between curvature and circumferential drift, OCT scans of 4 constant curvature channels were performed. The angle of each image would be calculated, as shown here, and the change in image angle across the image stack would quantify the effects of curvature. First, an image was viewed in its polar form, as shown here. A peak intensity depth profile of this image shows the region we want to identify as the U-shaped spot in this bottom corner. Depths were then profiled based on their intensity and Cartesian location. Their Cartesian location was necessary in order to group points along this yellow line to avoid trying to calculate the angle using outlier points. Endpoints along this line could then be used to form a line which would be used to calculate the angle of the image. The algorithm was validated by choosing 50 images at random and calculating the angle in those images using points identified by hand. A bland Altman plot and a lens concordance correlation coefficient were used to show strong agreement between the algorithm and the gold standard set by the manual inspection. Finally, a formula relating curvature to circumferential drift was derived by plotting circumferential drift versus curvature and determining a line of best fit through these points. The equation for the line of best fit is the equation that relates curvature to circumferential drift. In conclusion, circumferential drifts were observed when reconstructing a stent using clinical imaging data. In this project, I successfully developed and validated an algorithm that calculated the angle of each image, which was then used to derive a relationship between curvature and circumferential drift. Future work will update the existing framework to adjust OCT images to counteract the effects of circumferential drift.